Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh and good day everyone. So today we are going to continue our lesson on chapter 7, energy of a system. Right? So first thing first, before we consider the energy, we need to define what is system means. Okay, system could consist of few objects, okay, that interact with one to another. For example, okay, we have two blocks here, okay, are moving, okay, with some certain amount of acceleration, okay, the same amount of acceleration, and are connected by a rope. Okay, then environment is the pulley, is the incline. Okay, so the surrounding, right, that is the environment. Okay, so what is work? So from this diagram we know that M2 is the one that doing the work, because M2 is the one that causing M1 to move up, right? So in this system, okay, the work done by M2 is transferred into M1 in terms of change in position of the M1. So there is energy transfer from M2 to M1. So in simple, we can say that work is an energy transfer. Okay, for this case is in terms of mechanical energy transfer. So let's observe this diagram where we have a duster, right, on a tray. Okay, so by applying different position or direction of force, okay, let's consider the applied force coming from the hand here, okay, the finger here, is constant amount and the same, right? But they are different in terms of direction. So based on our experience, okay, figure B, okay, this direction of force applied to the duster will cause the motion of the duster easier in comparison to A. Alright, and for B, for the C, and for C, okay, when we apply the forces perpendicular to the duster, okay, we cannot move the duster along the track here. Okay, why is it so? So it means that it's not only how much applied force to the duster, how much the distance traveled by the duster when we apply the force. It also depends on the angle between the distance traveled, the displacement experienced by the duster, and also the angle, the applied force. Okay, so in this case, it means that, okay, if we evaluate or transfer our duster into a simple object, right? So let's say the duster going to be displaced in terms of this direction. This is the displacement experienced by the duster, and here is the applied force, okay, by the hand on the duster. So the angle between them, right, does affect, okay, the amount of work done. Right, from here, okay, work done is actually, in terms of math, is a scalar product of two vectors. What are the vectors? The position vectors and also the force applied. Okay, so talking about math of a scalar product, when we have A, okay, to have a scalar product, we have to have the dot process between two vectors. Okay, so whenever you have vector A dot with vector B, okay, it's equivalent to AB cos theta, and theta here must be the smallest angle between these two vectors. Okay, so this is actually similar to this one, okay, where we have work done is equivalent to F delta R or X just now, okay, cos theta. Okay, well, this is actually in math is equivalent to F dot with the delta R. Okay, so back to our diagram just now. This is our object. Here is our delta X. And here is our applied force just now, right? To make it easy, we can transform the F here because we want to figure out the smallest angle between the force and the displacement. So the angle going to be this one, no more here. Okay, we already transfer it to that. So the angle, the smallest angle between the displacement delta X, okay, and the F is this one. So based on this, we are going to have work done is equivalent to F, actually by math, is like this. In terms of magnitude of it, meaning of it, okay, provided that theta must be the smallest angle between the X and the F. Alright. This is what we call simple free body diagram for the object being applied force on it and there is work done happen to it. Okay, so now how about if the F applied is in terms of this direction? Okay, so again the same, it's work done equivalent to F delta R cos theta. So this is the displacement of the object. Okay, from initial point to the final point we have delta R, and the angle between the R, if we can imagine the R is here. Okay, so this is the smallest angle between the F and the delta R, right? So this is again actually in terms of math is F dot delta R. It's a dot product we call it. When we multiple two kind of vector and the product is scalar, so the multiplication between these two vectors known as dot product. Okay, so we are now considering the force applied from the beginning of the topic until now. Okay, the force is a kind of a constant force, right? So as we know, the object when we place on the floor, okay, we have weight, we also have normal, but just now we only consider the work done by the F. Why is it so? Because okay, between the delta R and the normal, okay, the angle is, the smallest angle is 90 degree. Let me show you a simple free body diagram. Between normal, this is our object, this is our normal force, and here is our delta R. So the smallest angle is 90 degree. When you calculate work done by the normal force, it's normal force delta R cos 90, give you 0. 0 work done by the normal force. Now let's consider the weight. This is our object. The weight is downward. Our delta R is to the right. So the smallest angle between them is 90 degree. So again, work done by the weight is equivalent to weight delta R cos 90. So give you also 0. Okay, so in this case, in this situation, the only work done exists is due to the F applied, okay, which is equivalent to this. And the unit of the work done here is Newton dot meter, or known as well in joule. This is a SI unit, okay? What does that mean by joule? This is equivalent to Newton dot meter. And what does that mean by joule? Also can be placed or write up in terms of kilogram dot meter squared per second squared. Okay. If let's say, okay, the angle between the F and the R is 0. So what will happen? Okay. So work done will be work done due to the F or coming from the F on the block or object is F delta R cos 0, which give you, this is amount of it 1. So F delta R maximum value. What about the angle if the theta is let's say 180 degree? For 90 degree you already can see from here, right? If it is 180 degree, okay, then the work done will be F delta R, okay, cos 180 degree. So this give you 1. Then the work done going to have negative, okay, delta R. What does that mean by negative? Okay, the work done on the object is negative. It means that the object is losing its energy. Okay, if it is positive, the system or the object is gaining the energy because the work is done on it. Okay, that is the meaning. So now example 7.1, a man clean a floor, pulls a vacuum cleaner with a force of magnitude of 50 Newton at an angle of 30 degree with the horizontal. Calculate the work done by the force on the vacuum cleaner as the vacuum cleaner is displaced 3 meters to the right. So let's consider the force applied by the man is 50 Newton in this direction. Okay, and we know that we have normal, okay, we have weight, okay, experienced by the vacuum. Alright, and the angle here 30 degree and the displacement to the right, okay, is 3 meters. So from that, okay, we are going to use work done equivalent to FR cos theta. So cos 30, because if you want to put a simple free body diagram of our vacuum cleaner, right? So we have applied force here, okay, by the man, and here is the delta R. So the angle here 30 degree. Okay, hopefully you can visualize this. You can come up with a simple free body diagram to ease your calculation. So the amount of the work done by the man on the vacuum cleaner is 130 joule. What about work done by the normal? Again, normal and delta R. So it's 90 degree. So work done by the normal force will be 0. How about the weight? Weight downward. The displacement position vector is R, also 90 degree. So work done by the weight, also 0. If the question asking for, let's say, the W net, okay, on the vacuum cleaner. So W net must be work done coming from the F applied by the person plus work done by the normal plus work done by the weight, which give you this one 0, this one also 0, which is equivalent to 130 joules. This is on how to answer if the question asking for W net. So now we are going to take a look in detail about the scalar product of two vectors. As I mentioned just now, okay, A dot B is equivalent to AB cos theta, and the theta must be the smallest angle between vector A and vector B. So for the dot product, okay, it can apply the commutative law, okay, where we have A dot B is equivalent to B dot A, okay. And then it also can be used with the multiplication law, okay, where we have, if let's say we have A dot parenthesis B plus C, we can open up the bracket or parenthesis here to A dot B plus A dot C, right? And because we are applying cos theta between A and B due to dot product, okay, if it is perpendicular where the theta is 90 degree, A dot B will be 0 because cos 90, okay, because A, B, cos 90 degree, so this is 0, right? And if the A is parallel, okay, parallel to the B, right, then the angle will be 0. How is it? Okay, this is the object, let's say. This is the point considered. This is the A. This is also the B. So the angle between them, 0. So if that's the case, you will have AB cos, okay, 0. Give you 1. So you are left with AB. Then if it is anti-parallel, how is it? We can visualize it like this. This is A, this is B. Okay, they are anti-parallel or 180 degree in terms of angle. So you will have AB cos 180 degree give you this one, -1, negative AB. Right. So, okay, what does that mean by this diagram? Okay, where we have this is vector A and this is vector B. When you are doing dot product between A to the B, it means that we are looking for a projection of the B. Projection of the B is B cos theta onto A. Okay, then we multiply them. That is the meaning, right? So, since we are dealing with vectors, okay, there are another information about dot product of the vector units. Okay, so, okay, it just like a formula, okay, math formula. So, I dot I is equivalent to J dot J is equivalent to K dot K, which is the amount of them is 1. But if I dot J or J dot I or J dot K, okay, the amount of them equivalent to 0, has no meaning, has no value. Okay, the one that give value only I dot I, J dot J or K dot K equivalent to 1. So if let's say you have vector A, as we know, within vector A, it has component, okay, in terms of X component, J component and K component, right? Goes the same to the vector B. If we are doing A dot B, it means, okay, we have to multiple A and B in terms of X. Where is the I? Okay, the I become 1 because I dot I dot I become 1. So it is not written here anymore. Right, and J dot J also become 1. So it is not written here anymore. Okay, hopefully you get this idea. How about if we have A dot A? So again, we are going to have just like A multiple with A, AX. Okay, so you have AX square. Okay, it just like AY multiple with AY. So you will have AY square. Goes the same to the Z. So in terms of magnitude, it's actually A square. Okay, example 7.2, the scalar product. Okay, vector A and B are given by this, right? determine the scalar product of A dot B. So remember, we have to collect the same, okay, simple as it can be, you collect the same I, okay, multiple with the I, because the rest, if you put I cross J, I multiple with the J, okay, and I multiple with the K, you will get zero amount, still remember. Okay, so now what we have here, I, 2, for A, you have 2 in term of I, right? And then 3 in term of J, positive 3. For B, you have negative 1 and positive, negative 1I, positive 2J. So you are going to do the dot product between them. Okay. My suggestion, you don't have to consider I dot J or J dot I, because it's going to give you 0 meaning. Right? Straight away, use I dot I and J dot J. So you have here 2I dot negative I. So you will have negative 1. Right? And then this one becomes 0, this one becomes 0, and then you have 3, okay, dot 2, multiple with 2. So it means that how much? 6, positive. Okay, so you will have negative 2, okay, positive 6. So means that the product of it is 4. Okay, or it simply can be done also in terms of this way. Okay, you just dot between or multiple between X component and Y component. Alright, so it goes the same. So find the angle between A and B. Okay, so since we have, okay, this is to figure out magnitude for each of the vector A and vector B. Okay, then we have just now, by definition, A dot B is equivalent to AB cos theta. So if we want to have the theta, cos theta is equivalent to A dot B, okay, over AB. Okay, A dot B just now we have 4. Okay, and A times B is magnitude of A times magnitude with of the B. So you have square root of 13 multiple with square root of 5. So you have 4 over square root 65. Okay, and then you can figure out the theta. Okay, which is 60.3 degree. Right. 7.3, work done by constant force. A particle moving in the xy plane undergoes a displacement given by r equivalent to this, 2I 3J meter, as a constant force of 5I plus 2J Newton acts on the particle. Calculate the work done by F on the particle. Okay, so given to us, okay, the force is in terms of Ij, the position vector as well in terms of Ij. We have to figure out the work done. Right. So, okay, work done is equivalent to, by definition, is F dot delta R. Okay, so what is our F here? Okay, and this is our R. So again, remember, okay, no need to consider I dot J, because the product will be 0, or J dot I. Straight away, okay, it's I dot I, which is 5I multiple with 2I. This one, you will get 10. Okay, the product of the meter here, 0, 0. And then 2J dot with 3J, you will get 6J. And J dot J will become 1. So left with 6. So 10 plus 6 is 16 Newton dot meter or joule. Okay, this is the amount of work done, okay, by the F on the particle. So let's move to work done by a varying force. Okay, just now, remember, from the beginning until just now, we are talking about work done by a constant force. The amount of the force constant throughout the process. Okay, but now we are going to move to work done by a varying force. What does that mean? Varying force means that the force keep on changing. It's not a constant value. Okay, so we are not going to apply the formula of F delta X directly. Cannot be done here because our F right now is a kind of varying force. Okay, it's not a constant, so you cannot use this formula anymore. So how is it going to be? Okay, let's say, okay, you have a diagram of force. Okay, cut that part. So now, okay, we are going to take a look. For example, okay, you have a force in terms of curve like this. When you have F versus X, means that your F is keep on changing with the position. So if this kind of situation, to calculate work done is actually equivalent to F times with the X, isn't it? Delta X. It means that we are going to calculate area under the graph. That is equivalent to work done. But, okay, we may do part by part. We may calculate it part by part. Okay, part by part like this, a small part. And then add up together. That will give you also the amount of total area or work done. Okay. We have another way to do it in terms of math. Okay, we can put it integrand. Okay, integrand of the f(x) as a function of dx. Okay, this is the same meaning of this, right? So from x initial up to x final, okay, we can do integration of fx to the respect of x from initial to final position of x. Instead of calculate box or part by part like this, we can do it in terms of mathematical formula or integrate the function of fx, okay, to the respect of x from initial to the final x. So work done, the sum of the work done, okay, the total work done on the system must be coming from external agent, right? On the system, we are the one that doing the work on the object. Okay, must be equivalent to of integration of all the f, okay, experienced by the object as a function of x to the respect of x from initial up to final position. So for this situation, this is actually for particle. The object is particle. Alright. So we can rearrange this one. Instead of using only x, we may put it in general dr because it could move in x and y. It could have a change in x and y position, okay, at the same time. So it is better to place dr. Okay, but then if our system is deformable system, for example a balloon, okay, when you squeeze the balloon, okay, it's deformed, isn't it? So for deformable system, okay, to calculate the total work done on the system or work done by the external agent on the system, we may calculate the sum of, okay, for each of the force to the respect of the position. Okay, so part by part. Okay, in other words, 7.4 Calculating total work done from a graph. Okay, given to us now, graph of fx versus x. Okay, let's read the statement. A force acting on a particle varies with x as shown in the figure. Calculate the work done by the force on the particle as it moves from 0 to 6 meter. So from here, from the beginning up to 6 meter position. So means that we need to calculate area under the curve, right? So we cut it into parts. Okay, so where we going to consider work done for A to B. So here, okay, the first area. So you have 5 Newton times with a 4 meter. So you have 20 joules or Newton dot meter. So from B to C, this is a triangle, right? Okay, then you have half times with 5, okay, and then times with 6 minus 4, 2 meter. So you have 5 joule. So from A up to C or W net must be a combination or add up, total up. So you have 25 joules. Alright, let's take a look on a model where we are going to observe work done by a spring. Because the force within the spring is a kind of varying force to the respect of position. Okay, so let's take a look on this. We have a spring, okay, and attached to the block, okay, placed on horizontal surface where there is no friction at all. So the block is displaced from equilibrium position or x equivalent to 0 to the right until it reach amount of x displacement to the right. So at this instant, okay, we are going to release the block. The block going to be moved to the left by spring force Fs. So bear in mind just now, okay, the displacement that we do on the block is to the right. However, the spring force is to the left, right? It caused the block to move to reach equilibrium position. So to restore its initial position, that is why spring force also known as restoring force. Once the block reach the equilibrium position, okay, the spring force is 0 right now. However, due to the conservation of momentum, the block going to proceed in motion to the left, right, until the perfect case is it reach maximum displacement of x but in left direction, right, and then it stop a moment. Okay, whenever it stop a moment, the spring force exists again, okay, and it's going to move the block to the right in opposite to the initial displacement just now, which is to the left, right? So from here, okay, let's recall the behavior of the spring force is explained by Hooke's law. This is Hooke's law. It's saying that the spring force or restoring force within the spring is directly proportional to the displacement of x but in opposite direction. The k here is a constant known as spring constant or force constant, or also known as stiffness of the spring. Alright, and the unit of the k must be Newton over meter. Okay, so if we sketch, okay, a graph of Fs versus x, okay, for this situation of mass spring system moving back and fro, so we can have this kind of graph, right? So if we refer to this graph, okay, area under the curve will represent the magnitude of the work done, okay, work done on the system by the spring force. Okay, so if you refer here, it is a triangle, right? Okay, so the formula going to be a triangle, area for a triangle. So work done by the spring, Fs must be half of Fs itself times with the x because it's a triangle. So Fs itself is negative kx times with the x. So we will have negative half kx squared. Right, so this is work done by the spring force, okay, in terms of simple way, right? And bear in mind all the time that our Fs is a kind of vector. So it has, in this information from Hooke's law here, it has only x or I component, okay, but Fs itself. Alright, so all the time we also can treat our Fs in terms of I component, ijk component, but for this situation, our Fs is completely along I or x component, and the magnitude of Fs itself is negative kx, right? So if let's say we want to treat in terms of mathematical treatment or vector technique, okay, we also can have work done by the spring, by the Fs, is in terms of integration of F, okay, to the respect of position vector dr, right? So starting from initial up to final position. Okay, so if we see here, our Fs is negative kx I dot, remember, work done is a scalar quantity, so it's applied, dot product, okay, dot dx I, okay, for the situation given here, right? So starting from negative x maximum up to 0, okay, we are taking on our from the position here up to this, right? So okay, we integrate this one, we will get half kx maximum square. How to have this? Okay, based on this x power n, okay, because k is a constant, right? So in terms of how to integrate the x, okay, x power n to the respect of dx. So how we are going to integrate this is n plus 1, okay, over the n plus 1. So that is how we manage to get the formula of work done by the spring is equivalent to half kx maximum square. Actually, this is similar to the one that I showed you just now. Alright, which is, we can conclude that, okay, so work done, okay, by the spring force on the block as it moves from negative x maximum to 0, okay, for this side, okay, is the area of the shaded triangle, right, which is half kx maximum squared, right? So if we want to put it in general, so work done by the spring force on the block is equivalent to integrand of the Fs, the negative kx, to the respect of dx from the beginning, x initial, up to the x final. So if this is the case, then work done by the spring is half kx initial squared minus half kx final squared. So if you see here, it's initial minus final. Okay, so this is work done by the spring on the block. So if we are talking about F applied now, okay, in other way or opposite, F applied is always, okay, opposite to the spring force. Remember, we displaced the block initially to the right, but the spring force bring or try to restore the position of the spring and the block to the left. Okay, so it's always same magnitude but in opposite direction. So negative of negative kx, okay, will give us positive kxi. This is F applied. So work done by external forces, or external agent, okay, on the block must be integrand of F applied, okay, to the respect of position vector dr, right, from initial up to final point. So F applied here is equivalent to positive kx, okay, dot dxi. So from here, okay, if for this situation from negative x maximum up to 0 position, we are going to have negative half kx maximum squared. So in general, right, work done by external forces on the block, okay, and the mass spring system, okay, is equivalent to half kx final square minus half kx initial square. What we can conclude here is work done by the spring is equivalent to negative of work done by the external force, right? So work done by the spring just now, okay, is half kx initial square minus half kx final square, right, which is negative of half kx final square, okay, minus half kx initial square, isn't it? Tally, right? Okay. So example 7.5, measuring K for a spring. Okay, a common technique used to measure the force constant of a spring is demonstrated by the setup in the figure. The spring is hung vertically and an object of a mass m is attached to its lower end. Under the action of the load mg due to the weight, the spring stretch a distance d from its equilibrium position. Okay, so the d is the elongation, okay, due to the weight of the object. A, if a spring is stretched 2 cm by a suspended object having a mass of 0.55 kg, what is the force constant of the spring? So we want to determine the K. Alright. So in this case, this is our object just now. It has weight downward and it has spring force upward. So from here, summation of Fy equivalent to, okay, it's not in motion yet, right? So equivalent to MA and the A is 0. Okay, AY, okay. So Fs plus mg must equivalent to 0. Fs is upward, positive, based on this setting. Okay, and mg is downward, negative, equivalent to 0. Then from here, we know that Fs is equivalent to mg. Then Fs itself is equivalent to Kx, right? Fs equivalent to Kx in terms of magnitude, okay? The direction already considered here, right? So because we already considered the direction within this part, right? So, okay, is equivalent to mg. So let's rearrange. For this case, it's using x as d, right? So you're going to have, okay, k d equivalent to mg. So if you want to figure out the stiffness of the spring only, then it's mg over d. Okay, the x is d in this case. So substitute the rest of the information given, then you will get your K is 2.7 times 10 to the power of 2 Newton per meter. B, how much work is done by the spring on the object as it stretches through this distance? So as we know, work done by the spring is equivalent to half kx initial square minus half kx final square, right? So this is coming from half kx initial square minus half kx final square. And our x initial is equilibrium position. That is why it's 0. And our x final, okay, is the D. Right. Then the formula will be simplified into this. Then you may now substitute the value of the K and also the D. It gives you the final answer of this. Okay, now evaluate the work done by the gravitational force on the object. So if we're talking about work done by the gravitational force, it means that work done by the weight or mg. Right? So based on the same concept of F dot delta R, now our F is mg, our R is the D, okay, and then angle between, okay, the weight and the displacement is 0. How come? Because of this. This is our bob just now, okay. The weight is downward, right? The D also downward. That is why the angle between, okay, the weight and the D is 0 degree. Okay, which cos 0 give you value of 1. Right, that is why finally this formula become mgt only. So you will have this amount of work done by the weight on the spring.